Hello everyone, so today I'm going to talk about the Fibonacci numbers and how to find the formula for the Fibonacci numbers using matrices. So the Fibonacci numbers are defined recurrently, so we define that f1 is equal to 1, then f2 is equal to also 1, and then fn plus 2 is equal to fn plus fn plus 1. So now we have a problem how to find fn, like to express it in terms of n. Okay, so let's rewrite this recurrent relation using matrices. So we consider the two vectors. So first we have the vector fn plus 2 fn plus 1, and then we have the vector fn plus 1 fn, and we notice that we can express it using the matrix multiplication. So if we introduce this matrix 1 1 1 0, we write, so this is multiplication. So then we notice that when we multiply the first row in the matrix by this vector, then we get exactly this formula. So we get fn plus 1 plus fn, and this would be equal to exactly this number. And when we multiply the second row in the matrix by this vector, then we get fn plus 1, and the second fn is multiplied by 0, so it would be 0. So the bottom row in the matrix multiplied by this vector would be fn plus 1, this exactly the second element in this vector. So this formula holds. So now we notice that the second, and this is a kind of also a recurrent relation, but the second, this vector can be also expressed using the same formula, basically like this. So we denote this matrix by A, just not to repeat it everywhere, and this would be equal to A, then multiplied by another A, and the vector fn minus 1, right? So so then we can write that this would be equal to, so this is A squared, right? So then we rewrite this vector again. This would be A cubed by the vector fn minus 1 fn minus 2, and so on. And finally we would get A to the power of n, f1 f2, f2 f1 f2 f1, right? So now let's Now let's remove everything that we don't need. So we have this formula basically fn plus 2 fn plus 1 equal to this, and the matrix A is equal to 1 1 1 0. Okay, so this is actually already a formula. So like we already expressed fn plus 1 fn plus 2 in terms of this matrix A, and by the way, f1 we can rewrite it further, so it's a to the power of n 1 1, because f1 and f2 they're just equal to 1. Or let me actually put here. Yeah, so this is already in a way a formula for fn plus 2 and fn plus 1, but of course we don't know like how to raise this matrix to the power n. So, and this is kind of the problem now. So we reduced the problem of finding the formula to the problem of raising this matrix A to the power n. So let's so like there are ways in linear algebra how to raise a matrix to the power. So we need to diagonalize this matrix if it's possible. If not, like we would find the Jordan normal form of the matrix, and then we would, then it would be much easier to raise it to the power. So for that we need to find the eigenvalues of this matrix. So let's do it. So eigenvalues are defined as so we have matrix A multiplied by eigenvector V should be equal to lambda, which is eigenvalue multiplied by the same vector V. This can be rewritten as A minus lambda I multiplied by V is equal to 0, and to find such lambda we need to calculate the determinant of A minus lambda I should be 0. So the matrix A minus lambda I is 1 minus lambda 1 1 minus lambda, and this determinant is equal to 1 minus lambda multiplied by minus lambda. So take the product of the values on the main diagonal minus the product of the other two numbers, so minus 1 multiplied by 1 equals 0, and this is can be written as lambda squared minus lambda squared minus lambda minus 1 is equal to 0. So this is a quadratic equation. Like, I'm not going to show in detail how to solve it. It's a straightforward problem, and there are two roots in this equation. One root is lambda 1 is equal to 1 minus square root of 5 over 2. And the other root is lambda 2 1 plus square root of 5 over 2. So now we need to find the these are two eigenvalues, so we see that they are different. Now we need to find the eigenvectors. So for that, so for example, for lambda 1, so eigenvectors can be found. So we return to the previous equation. So it was a minus lambda 1 I multiplied by the vector v1 eigenvector should be equal to 0. So this matrix we already know. Like we have put the value lambda 1 here, and vector v1, like it has two values in it, and this would be basically a system of equation in two variables. Can be easily solved. Like, I'm not going to show the details. It's a very technical, straightforward thing. So we can find that v1 is equal to 1 minus square root of 5 divided by 2 and 1. So it has two elements, first element, the second element. And similarly we can find v2. It would be 1 plus square root of 5 over 2 and 1. So we found the eigenvectors and eigenvalue. So now we can write the matrix. Because they're different, so we know that the Jordan normal form would be a diagonal. So this matrix is diagonalizable, and if we write that matrix A is equal to S then the diagonal matrix lambda 1, lambda 2, 0, 0. Here it will be S to the power minus 1, and the matrix S, it has the columns of the matrix S will be exactly the eigenvectors. So the S will consist of columns v1 and v2, and S to the power of minus 1, like we need to invert this matrix. We can also I'm not going to show the details, it's not very difficult. So the matrix S to the power minus 1, it's this matrix. Minus 1 over square root of 5, 5 plus square root of 5 over 10, 1 over square root of 5, 5 minus square root of 5 over 10. Okay, so basically we represented the matrix as we diagonalized basically matrix A in this form. We know matrices S and S to the power minus 1, and we know this diagonal matrix. So now to find A to the power of n, we simply write that this is S, so let's denote this diagonal matrix as D. Okay, ST, S to the power minus 1, and again ST, S to the power minus 1, and so on. ST, S to the power minus 1, so total we have n times. So we notice that this S to the power minus 1 and S, when we bring this together, they cancel each other, right? So this cancels, then this S to the power minus 1 and cancels with the next one, and so on, and this would be cancelled with the previous one. So in total this would be equal to S G to the power n, S to the power minus 1. Yeah. Right, so here we know all the matrices already, and d to the power n, so this would be equal to S m1 to the power n, m2 to the power n, 0, 0, S minus 1. Basically, that's already the formula that we needed. So, like we can substitute the known numbers. So we know both lambda 1, lambda 2. We know S. We know S to the power minus 1. So we basically found the this A to the power of n. And when we substituted, we find the vector Fn. Yeah, so basically using this formula we found this, we can express Fn plus 1 and Fn plus 2 this way. Okay, so let's simplify this expression. So now we need to rewrite the matrices S and S to the power minus 1 in terms of lambda 1 and lambda 2. So let's return here. So we see that the matrix S is equal to this. So it's V1 and V2, where V1 and V2 are the eigenvectors. So this one and this one, and we notice that they already contain lambda 1 and lambda 2. So because this expression is exactly lambda 1, and this expression is exactly lambda 2. Okay, so so basically this matrix S now can be rewritten as S is equal to lambda 1 1, lambda 2 1, like this. Okay, and now the matrix S to the power minus 1, here we have it. So this expression also can be rewritten. So we notice that that 5, so this basically can be expressed as this can be expressed as lambda 2. Well, so okay, let's find it separately. So 5 plus square root of 5 divided by 10. So let's divide both numerator and denominator by the square root of 5. Then we have 2 square root of 5, and here square root of 5 plus 1. Okay, and this, so notice that this is exactly lambda 2. So it's lambda 2 divided by square root of 5. Or we can also express it, and we would need it better, because lambda 2 and lambda 1 are connected to each other, and particular, so their product is equal to either minus 1 or 1, I can't remember now, but their sum is equal to 1. So this can be also expressed as 1 minus lambda 1 divided by square root of 5. Okay, that's what we would need, and similarly we can express the this expression here. So after this simplification, we can write this matrix S to the power minus 1 is equal to 1 over square root of 5. We move it here, and here we have minus 1 1 lambda 2 minus lambda 1, or we would need another form. So we would need another form, 1 over square root of 5 minus 1 1 1 minus lambda 1 minus 1 plus lambda 2. Okay, so now we replace the expression. So let me remove this. So now we write that this is equal to 1 over square root of 5. So this comes from from this. Then matrix S, which is lambda 1, 1, lambda 2, 1. Then lambda 1 to the power n, lambda 2 to the power n, 0, 0. And then the matrix S to the power minus 1 with already the multiplier 1 over square root of 5 is already here. So this would be minus 1, 1, 1 minus lambda 1, minus 1 plus lambda 2. Okay. Now we rewrite this as so we multiply the first two matrices, this by this, so lambda 1 would be lambda 1 to the power n plus 1, this by 0 would be 0, so then the first row by the second column it would be lambda 1 by 0 is 0, lambda 2 lambda 2 to the power n plus 1, and the bottom row would be lambda 1 to the power n, lambda 2 to the power n. Okay, this we just rewrite. Okay. Now let's multiply these two matrices, so it would be minus lambda 1 power n plus 1 plus lambda 2 to the power n plus 1 here it would be lambda 1 power n plus 1 minus lambda 1 to the power n plus 2 minus lambda 2 to the power n plus 1 plus lambda 2 to the power n plus 2. Okay, the bottom row is minus lambda 1 power n plus lambda 2 to the power n, and here it would be lambda 1 to the power n minus lambda 1 to the power n minus 1 n plus 1, excuse me, n plus 1 minus lambda 2 to the power n plus lambda 2 to the power n plus 1. Okay, and now we recall that the main formula. Where is it? Yeah, so we recall this formula. So to find, basically to find f n plus 1, it would be the when we multiply this matrix by this vector, it would be basically the sum of the elements in the bottom row of this matrix, right? Because when we multiply the bottom row by this vector, it would be 1, 1, so it would be the sum of the bottom two elements, and we would get f plus 1. So let's go back. So this is the expression. Remember that this is the expression for a to the power n, right? So f n plus 1 would be equal to 1 over square root of 5, and here it should be the sum of the bottom two elements in this matrix. So it will be minus lambda 1 to the power n plus lambda 2 to the power n plus lambda 1 to the power n minus lambda 1 to the power n plus 1 minus lambda 2 to the power n plus lambda 2 to the power n plus 1. Okay. And here we see that, so let me write it more carefully. Okay, so now we see that this and this cancel each other, and this and this cancel each other. Okay, so what remains is 1 over square root of 5 basically lambda 2, okay, lambda 2 to the power n plus 1 minus lambda 1 to the power n plus 1. And this is almost what we need. So now we can just rewrite it a little more. So this is the formula for fn plus 1, but just for convenience we actually need fn, so we replace n plus 1 with n, so fn then would be equal to 1 over square root of 5 lambda 2 to the power n minus lambda 1 to the power n. Okay, and this is basically the formula. We can, just to be complete, we can replace the values of the eigenvalues, so it would be 1 over square root of 5. Here it's 1 plus square root of 5 divided by 2 to the power n minus 1 minus square root of 5 divided by 2 to the power n. And this is the final formula that we need. Notice that even though it's expressed in the square root of 5, it's actually an integer number, a natural number for every n. Yeah, so basically that's it.